And I'm Jonathan Stevens. I'm a nuclear engineer, been one for going on 25 years now. I started my career at what is now the Naval Nuclear Lab, designing naval reactors. Later on, I worked for Arrivo, which our European guests will have heard of for quite a while. And now I work for BWXT, best known as the company that manufactures all of the naval reactors for the US Navy. But I'll have a little bit more on the company in a second. So some of this will be familiar to you. I kind of wanted to set the stage from my perspective as an outsider to the maritime industry. But we have these IMO decarbonization goals, and you'll recognize that this is already out of date. About a week after I put this little picture together, they made the goals more aggressive. And now, of course, the objective is to try to decarbonize completely by 2050. And that's obviously a very aggressive target. Some people would say unrealistic. But I was curious, could you in fact do that? And when as I did some research, I really could only identify a couple of ways to actually achieve 100% decarbonization of maritime shipping, certainly if you're looking at the very large ships. And that would be using e-fuels, and that really only counts if you're generating them with zero carbon energy. So people tend to assume renewable energy for that. Or if you could generate energy on ship in an emissions-free manner. So with that, I kind of look at those two options in a little bit more detail. So on the left, I've got the idea of producing e-fuels using nuclear energy. And the reason I say nuclear energy is far and away the largest emissions-free source of energy that exists. When we're talking about e-fuels, and you consider that there's a considerable amount of energy lost in the creation and transportation and eventual combustion of those fuels. And the volumes of e-fuels that we're talking about for some of these large ships, there simply is not, if you run the numbers, and I have, you cannot realistically generate that level of hydrogen or ammonia with renewable energy. It simply doesn't have a sufficient energy density to do that. Really, the only way to do it is with nuclear energy. Another thing to consider, another potential drawback, if you look at this figure on the left, I've drawn essentially equivalent fuel volumes, depending on what type of fuel you're using for your vessel. And you can see that if you go to something like hydrogen or ammonia, it takes more than twice the space of current fuels to get the same amount of energy out of it. You'll also see, I did this kind of tongue-in-cheek, that you can't see anything at all for uranium. The reason is that uranium has an energy density of more than 1 million times fossil fuels. And so you literally would not see on this plot, in comparison to these tanks of fuel, the volume of uranium needed for the same amount of energy. On the right, I have the other alternative to consider, which is having an onboard nuclear electric plant. We know that onboard nuclear is doable because, of course, the Navy's been doing this for decades. It's zero emission, it's low noise because you're not combusting anything. The only noise would be the noise of the propellers themselves. It's a very small footprint on the ship, stable operational costs, so you don't need to worry about trying to predict what fuel is going to cost over the next 5 to 10 years, because when you load a nuclear reactor on, it has all the fuel it needs, all the uranium it needs for at least until it needs to be refueled, and I'll get into that a little bit more. We've heard some things about reducing energy use by lowering ship speeds, for example, with nuclear. Since it's emissions free, you could actually increase the ship speeds. I know that's more appealing to a lot of the people coming from a commercial standpoint, from shipping companies. Of course, you have the ability to redirect electric power to shore in your providing port power. We heard a little bit about that over the course of this conference, and I kind of like going near the end of the conference because I get to hear some of the earlier discussions and try to tie into some of them. With the ports, one of the interesting things I didn't hear come up during this conference was that they want to electrify, but a lot of these ports are in places that simply don't have the grid to support electrifying. And so nuclear-powered vessels is a very interesting potential solution to that. Now, of course, there are legal and regulatory challenges. There are reasons why we don't already have all of these nuclear ships out there, and I'll get into that a little bit as well. PWXT, just a little bit of information because a lot of people have not heard of us, and that's for good reason. For a long time, the only thing we did was manufacture U.S. naval reactors, and so there wasn't much reason to have a social media presence. And that is our our primary business, and that is still our main business. But we have gotten into microreactors, space reactors, and I'll show some examples of that in more recent times. But the main thing I want to point out is actually not on this slide specifically, but we have over the time of our existence manufactured over 400 nuclear reactors. A lot of people don't realize that there have been that many made. That's probably more than half of the reactors that have ever been constructed. Of course, mostly for the U.S. Navy over its history. We as a company have been around with one name or another for over 165 years now. You may have heard of Babcock and Wilcox or B&W. It's the name has changed a few times, but it's the same company. One thing I wish I'll have to put on a later iteration of the slide is that you heard about the NS Savannah yesterday. B&W made the manufacture of the reactor that was on the NS Savannah. So something we've been doing for a long time. I was on that. So what are we doing in our advanced technologies group today? This is when I talk about advanced technologies, which is the group that I'm in. That is everything that is not naval reactors. So we are distinct and independent from the naval reactors program because we have commitments there that we don't want to worry about impacting. So some of the projects we have going on, which you may or may not have heard of, one of them is Project Pele. This is for the Department of Defense. This is a 1 to 5 megawatt electric reactor, and we're not allowed to say anything much more than that because there is some classification restrictions around this. But the important thing to point out about it is this is a microreactor that is currently under construction. So when you may hear people say, well, advanced nuclear is a great idea, but it's too far off. It's not a true statement. We're building this reactor right now. In fact, the picture, you can see a picture of one of the vessel heads being forged right there. The other interesting thing about this concept is that it needs to be small enough and light enough to be transported for wherever the Department of Defense wants to use it. And so it actually fits inside a 20-foot Connex box and can be shipped by Air Force cargo plane. So it's very challenging because making a nuclear reactor of the power level we want in that size and mass is not an easy thing to do, but it certainly shows some of the capabilities that are. We have several projects in NASA space, nuclear thermal propulsion. I won't get in much to this other than to say, I find it fascinating that we are going to probably get a reactor into space before we get one in commercial maritime space. That commercial maritime really is kind of the final frontier. We are also working on microreactors for fission surface power. This is potentially related to the Artemis project, getting a base on the moon for eventually travel to Mars. And then finally, in the bottom right, I've got a DOE related project. It's got a few names, but I'll refer to it as Banner. That is a commercial microreactor meant to be as low cost as possible. No classification or anything around that, so it's one I can talk more about. It's also probably the most likely to be the basis for something that we would use in a commercial maritime environment. That is a high temperature gas reactor. It's 50 megawatts thermal per unit. So you figure 17 to 20 megawatts electric likely. Although a lot of the use cases we have for that are for the heat directly, not for electricity. In maritime space, it would be for electricity, for electric drive. And you could use one or multiple units in the concept. This won't be new to a lot of folks in the room here. Marine nuclear, civilian marine nuclear is not a new concept. We heard about the Savannah yesterday. 60 years ago, we had already put a commercial ship, nuclear powered ship on the sea. It's definitely a point of frustration in the nuclear industry that we've gone that long, seemingly having come up with a solution for emissions-free shipping. The ship, the Savannah, really was a success story. It did what it was supposed to do. It was never meant to be an economic demonstration, and so in fact, it was not economic, and that was one of the big reasons why it didn't didn't spawn a whole generation of nuclear commercial vessels. It was just a little bit too expensive to operate in a time when the alternatives were pretty cheap. And so I often wonder why, why is it that in 60 years we haven't gone back, and certainly we've looked at it, why have we not gone back to something like this? And I think, I don't know that this is the case. I think it's probably that we just haven't really had to make the decision to look at nuclear more seriously, because we haven't been so worried about decarbonization in particular. That really, I would say, is the big thing that's changed in recent years. Recently, we're seeing an enormous amount of interest. Oil companies, shipping companies, multiple a week are contacting us to ask about how would this stuff work. Maybe even a little more frustrating to me personally is that you look at the top left there, you'll see the Russians already have a nuclear-powered civilian ship. It's a cargo / icebreaker. They actually have some icebreakers as well. That is operating emissions-free already. They've already, I like to tell people, they've already solved the problem. Of all people, the Russians did. Now, there are some, certainly this has pointed out some of the difficulties of this. This ship broke down a few years ago off the southern coast of Africa and had to be towed all the way back to Russia because nobody along the way would allow them to put into port. It's hard to say how much of that is because it's the Russians versus it's a nuclear ship. But that is definitely one of the big concerns going forward, is how do you work through allowing a nuclear vessel into port? Of course, the Navy has to deal with that as well. But there are some differences there. So I didn't want to presume that folks knew what we're talking about when we're talking about nuclear power or nuclear propulsion. If you look at how nuclear propulsion works on how it works on a Savannah, it's a typical, this would be a pressurized water reactor here in this example. Oops. Pressurized water reactor in this example with some sort of steam generator coupled to a typical Rankine cycle where the turbine is directly driving the propeller. And I'll get into a little bit later that this is not likely what commercial vessels would look like, but this is kind of where we're starting from. And this is also where all the experience is. So almost the vast majority of vessels that are out there with nuclear reactors on them, military or otherwise, are pressurized water reactor type like this. That's where most of our experience is. So I put this slide in for Sergio specifically. He was at my last presentation and said, I really would like to see more on nuclear safety specific. I'm like, okay, that's a fair question. So when we talk about nuclear safety, there's really a few different concepts here. One of them has to do with criticality. So without getting into all the details of nuclear physics, the idea, the way nuclear energy works is you have neutrons out there. They're hitting uranium atoms, causing them to split and create energy. As well as part of the product of that reaction is more neutrons, and they cause more reactions. So you have this chain reaction of neutrons. The way you control a reactor is by making sure that the population of neutrons stays the same. So you're generating more than one neutron with each fission, but you only want one of them to make it to the next fission. So we'll keep it at the same power level as you're doing. We call that criticality. The reactor is critical at that point. So with nuclear safety, one of the things you have to be able to prove is that you can shut down that nuclear reaction when you need to. When there's any sort of potential accident, that you know that you can shut the reactor down. Chernobyl is a good example of a case where that didn't happen. That had to do with the design of the reactor. And it's something that in the Western world, we've had solved for quite a long time. Criticality is generally not an issue. And in fact, there has not been any sort of Chernobyl-style accident, because the way we design American reactors and any reactors you'll find in Europe have physical characteristics that make it impossible for them to go uncontrollably critical. The reason that is, it has to do with the temperatures of the reactor. As the temperature of the reactor heats up, the reaction moves in a direction of slowing itself down. So eventually, with enough increase in heat, it simply can't sustain itself. So that's the kind of criticality side. The one that most people think about when you think about, say, meltdowns, which has to do with the cage heat removal. So a nuclear reactor, when you shut it down, it's no longer, you control the fission reaction itself, but all of the fission products that you generated up to that point still need to decay away. And that generates a significant amount of energy. It's exponentially decaying, but initially it's a very high amount of energy. So after you shut a reactor down, it is still generating, say, 5% of the power that it was generating at full power. And so that you still need a way to remove that energy. If you don't remove that energy, then it has no place to go but heating up the reactor itself. And then in many meltdown scenarios, when it simply heats up enough that it melts the materials in the reactor. That is a meltdown is what happened at 3 Mile Island and Fukushima. These were cases where Fukushima in particular, they simply lost the capability to cool the core. The core was shut down. It was not critical, but they could not keep it cool. This is where the advanced, you often hear about advanced reactors or generation 4 reactors, sometimes people call them. This is where they really excel. So the idea there is, what if you designed a reactor that even if it didn't have cooling, had melting temperatures in its materials that were so high that the decay heat wouldn't be enough to heat it up to its melting temperature. And so you get a lot of these designs utilize ceramics, a lot of advanced materials. The melting temperatures are very, very high. And in that case, we like to call them walk-away safe, even though you would never actually walk away from them. But the idea is that if you lost the cooling to the reactor, we know we can shut it down from a criticality standpoint, but we can also analyze it and show that KB was not enough for the reactor to actually achieve its melting, to reach its melting point. So a lot of the designs you hear out there, this is something that PWRs is much more difficult to do in that case. So why you see a lot of concepts other than pressurized or boiling or any light water reactors in a lot of these futuristic concepts. I'll mention a little bit more about those. The last part about nuclear safety I put on here is radiation shielding. This simply has to do with during operation and certainly after operation, making sure that you have enough. You don't have neutrons escaping or gamma rays escaping, radiation of any type, and causing a biological dose to people in the vicinity. That's a problem that we generally solve. The shielding is a well understood concept. It's easy to model. It's an interesting fact about the Navy that submariners on our nuclear submarines actually receive less radiation dose than people in the public do. Does anybody know why that's the case? Right, because we, sitting here, are receiving radiation from space right now. We're receiving some radiation from ground, radon, things like that. When you're in the middle of the ocean turns out to be a terrific shield. And the reactor itself is so well shielded that sailors actually get less dose than average members of the public. So that's, you can be in relatively close proximity to a reactor, certainly within tens of meters for a long period of time and not receiving an appreciable dose. When you get into, if you look into some advanced nuclear reactors, you quickly find that there are a lot of technologies out there. And there's a lot of people have their favorites. There's a lot of startup companies looking at different ones. I like to try to clarify that we're kind of on a spectrum of maturity here when we talk about reactors. Like I said before, light water reactors, so PWRs, BWRs, far and away the most mature technology we got out there. They don't have some of the neat features that the new ones will have, but they have certainly in maritime space proven themselves out for a long time. I toss in high temperature gas reactors as mature technology. There's a number of those in operation, research reactors. The UK in particular has a great deal of experience for decades on high temperature gas reactors. Lately, molten salts has kind of been the hot topic, although this is by no means an all-inclusive list of technologies. But molten salt gets a lot of attention now, a lot of research going on there. People like them because they have some benefits in terms of refueling, continuous refueling, a lot of good safety features. They are probably 5 to 10 years behind where we want to be on a lot of this. If we look at some of these IMO targets, we've had experiments, and we've had molten salt react. I didn't want to get too much in the details on this, but the molten salt reactors they're talking about now have the fuel as part of the salt. That's a relatively new concept. Molten salt, where the salt is simply a coolant, that has been a little bit. Yeah, I could go on for hours on different types of reactors, but when we're talking about some of these IMO targets, one of the big questions I often get is how quickly can we do this? And the more mature technologies are the type of thing that with enough motivation you could do as early as the end of the decade. The molten salt ones are going to be middle of next decade, probably at best, I would say. Fusion, I didn't actually used to have on here, but that interestingly was one of the most frequent questions I've gotten is what about fusion? And I typically tell people just don't hold your breath on it. It's not certainly in the 2050 timeframe, you're not going to see commercial fusion reactors. So how will another question I get often is why can't we just take the Navy reactors and put them in commercial vessels? And there are a couple of good reasons for that. I didn't even put on here that the Navy just wouldn't like that because of the classified technology involved. But there's a couple other significant ones. One has to do with the enrichment of the fuel. So if you look at military reactors, most of them are still using highly enriched uranium, which means most of the uranium is the fissile U-235 isotope. That is a material that can be used to make bombs. And so the commercial industry is not allowed to use anything above 20% enriched. That's the cutoff. Most commercial reactors actually use 5% enriched fuel, which is called low enriched. But most of these advanced concepts are using an intermediate level that's right at about 20%. It's actually just below 20, so you can say it's not bomb grade. So the fuel is not the same. Because the fuel is not the same, you can't use the same reactor design that high enriched uranium concepts use. It also means they're not going to last as long. So while the navies can say, we have a ship that can go last the life of the ship without a single refueling, without using something like a continuous refueling concept, that's really not going to be likely to be the case with commercial systems. Commercial systems, you're going to see more like a 5 to 10 year refueling time. And I say refueling, it's probably going to be more like a battery swap out. You'll have the concept would be to be able to quickly remove a core, put another core in. And probably to somehow schedule that alongside planned ship overhauls or something to that extent. That's an area clearly of interest from the economic standpoint for research. The other points I made on here is that commercial maritime plants are going to be almost certainly going to be nuclear electric, which means they're not going to be direct propulsion, shaft propulsion. There's a few reasons for that as well. Some of them are related to the classification of the technology to do that, but also because we want to decouple the reactor plant from the propeller for licensing and safety reasons. We don't want, for example, ship accidents involving damage to a propeller to have to result in consequences to the plant. It's easier just to decouple them. So it also takes away the ability, or at least some of the ability, to use the nuclear power plant for short power. One point I added on here, I actually just added on this because we heard a lot of talk yesterday about ways to reduce emissions on ships with sail technology. Some very cool stuff, a lot of stuff I have not heard of before. And I will say that is not mutually exclusive with using nuclear reactor plant on the ship. And the reason is, of course, most of these concepts that we talked about in the last couple of days do not fully decarbonize the ship. So there's still room to do that. And it's generally true of nuclear reactors that you can operate them at a lower power than they are rated for, and they will simply last longer. It's the same amount of fuel, you deploy the same amount of energy anyway. So if you have a 50 megawatt electric nuclear capability on the ship, and you're able to reduce the need for it down to 40 megawatts, reduce it by 20%, it will simply last 20% longer before it has to be refueled. So you could certainly implement multiple emissions reductions concepts on a single thing. This is not something that we need to replace them. This is just kind of a quick thing to show that this is, we've gotten so much interest from industry on how would this work? What's the next step to get a commercial reactor on the ship? And so we've started doing a lot of these systems architecture type workshops where we look, and I've taken the results of one and gotten all the proprietary stuff out, kind of simplified it a bit. But the idea is to show that we're already working with companies on how would the reactor as a system and its power conversion system and its power distribution work within the types of vessels that we're talking about putting these in. where would the boundaries be? Right. A lot of the questions out there are where do the nuclear regulations stop and marine regulations take over? Where do they overlap? We're looking with a number of different end customers on how that might work. Virtually all the concepts are turbine type. Yeah, and it's because that technology is reliable now and lower cost. A lot of the direct solid state conversion stuff simply doesn't have the efficiencies to make it work well. For things like space applications, there may be a use for it. Yes, in fact, a lot of historical space reactors that did use stuff. So there's a lot of challenges that are out there. Interestingly, they are generally not technical challenges that I like to point out. Clearly regulatory. In a lot of cases, there are laws, maritime laws that are outdated or non-existent. Jurisdictional questions. What point does whose laws do you fall under? There's an enormous amount of focus going on into addressing these questions, and I make reference to the MNAG group down at the bottom here. If you're interested in this topic, that group is kind of an interest group combined with national labs, Idaho National Lab, industry, maritime industry, nuclear industry, as to how we get through a lot of those questions of licensing. But of course, there's infrastructure, reactor handling. Which ports do we need to add capability, or even at sea capability to refuel these things? Uranium. There was a comment yesterday asking about security of supply of uranium. It is true that the biggest supplier of uranium in the world is Kazakhstan, though Canada and Australia are second and third behind that, and so there's not really a lot of concern over security of supply. I will say there is concern over where the enrichment capabilities are, because that is mostly in Russia. And so that has not escaped the minds of the folks at DOE, and so they have put a lot of effort into building up enrichment capability in the US. And so there are already companies spinning up capability in that area. I'm actually fairly confident that that's not going to limit us the availability of uranium or enriched uranium. I think that port access is going to be one of the tougher ones. Getting agreements, educating stakeholders, including the communities around them, which honestly have a lot to gain by allowing nuclear ships. They have a lot of pollution problems currently. Where we may end up is starting out with maybe a few key ports, probably ports in relatively safe areas, because security is obviously a question here too. And so I would say probably within US or US-UK routes are likely to be the first ones there, but that will be a challenge. Emergency planning, there's a lot of talk going on with how big a planning zone you need to have, even though the consequences of these are substantially less than the traditional power plants. You still need to have plans in place, at least within the immediate area. Personnel, was kind of hoping that some more of the students would stick around, because that's certainly a big question, is who will staff these things. There's a assumption, I think, right now that ex-Navy nukes will staff these, and there are simply not enough of them to do that if this really takes off in commercial space. And a lot of them already go off to operate our power producing plants in the US at least. So the merchant marine would be an obvious potential group of folks to train up and be the operators of these. You really don't need to be a nuclear engineer to be an operator, but you certainly need to have someone trained to be. And in fact, the merchant marine were the operators of the Savannah at this facility. So there's even precedent. One ship. Yeah, they were. I know part of the difficulty with that was that they had a very large crew. Part of the reason it wasn't economical, but I couldn't tell you right now exactly what the staffing levels would be. I will say that we have the capability of doing a significant amount of automation in nuclear space, because obviously these reactors that we are flying into space have no crew on them. So we have to be able to do that now. In all likelihood, we would have some available. And then I think maybe the bigger question is, what kind of physical security do you need to have on a commercial vessel? I think that's. Oh yes, you could, yeah. Economics, one of the difficulties with nuclear is the initial capital cost of it. You have almost no, and I won't say no, but you have very small operational costs because the fuel is all in there from the start. But the downside is all of the cost is up front, and that ends up being overwhelming in a lot of cases. And so that will, depending on the customer, and so that will require probably some creative way of doing things, whether it's leasing or things, that type of thing. And certainly the first few reactors will be very expensive, and that's where a lot of the initial use targets are government related, to kind of work our way down the cost curve there. And then, of course, waste management. What do you do with these when they're done? What's kind of been an ongoing challenge in the commercial nuclear industry in the U.S. right now. Most of the commercial plants still have all of their spent fuel on site. Nuclear engineers, geeky nuclear engineers, will tell you that's actually a great thing, because who else can tell you they've been generating electricity for 60 years, and the only waste has been a swimming pool with some casks in it, or dry casks out on pads. And in fact, spent fuel gets a reputation for being a lot more dangerous than it is. I've noticed this trend lately on YouTube of younger folks standing outside and hugging spent fuel canisters, dry casks out at these nuclear plants to show how they're really pretty benign. They're just there. You just need a place to put them. Now, someday, when we have the technology to break down the radioactivity of them, recycle them, there's some technology out there to do that now. But at the moment, it's just a matter of you need to let it cool down for a while in the pool, and then you just need a place to store it. And that's the case for commercial plants. That's what the Navy has to do. That's probably what we'll do for the foreseeable future. That said, all of the nuclear waste from power plants, the high-level nuclear waste that has ever been generated, fits, you could fit it in a single football field, maybe 6-7 meters deep, from every nuclear plant ever. It's really a very small, it is a certainly dangerous material, certainly a problem to be resolved, but it is not the problem that is often made out to be. So I will take any questions about